Okay, good morning. All right, we got quite a bit of things to go over today, so let's just jump right in. We'll look at 11.9. I'm going to get into the topic of how we can represent functions as a power series. And we're going to talk about why you would want to do that. There are many advantages to doing that, and you'll see a couple examples today. So we're going to start with a very simple series that we know a lot about, the geometric series. Right, so there's the geometric series. Remember, this is 1 plus r squared plus dot, dot, dot. And the nice thing about this is we know the sum of that. We know the sum is exactly 1 over 1 minus r. Okay? The first term over 1 minus the common ratio. And we know this converges if the absolute value of r is strictly less than 1. Now we're going to turn that into a function by getting a variable in here. So we change all of these r's to a variable x. So you see, then we get summation 0 to infinity, x to the n, which is 1 plus x squared plus x cubed plus dot, dot, dot. And we also know how to find the sum of that. Okay? And we know this will converge whenever the absolute value of x is less than 1. So this is the key equation we're going to be working with today. And we'll actually look at this from the right side to the left. We're going to start with a function that looks kind of like this and come up with a power series representation of that function looking like that. Okay? So here's the first example how we can do that. I have a function that looks quite a bit like what I started with, 1 over 1 minus x. So it looks like 1 over 5 plus x. We're going to take advantage of what's in the red box here to get a power series representation of this function. And to do that, we first have to notice that the bottom, the denominator, must be 1 minus something. Right now, of course, we have 5 plus something. We need to change this a little bit by doing a little bit of algebra. So we have 1 minus something, and then we apply that. Okay? So what we do here, let's factor a 1 over 5 out of this thing. So notice I took a 5 out of the denominator. And the leading term now becomes a 1. And then the original x, because I took out a 5, now is x over 5. And you can verify that if you multiply the 5 back into the denominator, we end up with this thing here, what we started with. So I'm almost there. I want this to be 1 minus something. I have 1 plus something. So we do this trick. We turn that into 1 minus the negative of that something. All right, so we have to have this form here. Whatever you started with in the denominator, you got to factor a constant out if needed, and then plus or minus, turn that into 1 minus something. All right, so let me copy that on this new sheet here, and then we'll do more to it. And from the previous page, we know 1 over 1 minus x is x to the n. And you can reuse that because x is a variable. As long as you change x accordingly on both sides, x can be anything. So in this case here, this will be the x in this equation. You see that? Yep, we're just doing algebra here, changing that to a new thing. So according to that equation, then we have 1 over 5 times the summation n from 0 to infinity, x to the n, but my x is now negative x over 5 to the n. Okay? Let's simplify this a little bit more. I'm going to write this explicitly as an alternating series by taking the minus 1 to the n out by itself. And then x to the n over 5 to the n. So think about what this looks like now. When n is 0, we have 1, 1, right? 1. When n is 1, we have minus x over 5. When n is 2, plus x squared over 25. When n is 3, minus x cubed over 125, and so on. Okay, and then this 1 over 5 out here, this is going to eventually go into here and multiply every single term by that additional 1 over 5. So in other words, the denominator really has 5 to the 1 more power. And if you look at this line here, we're going to bring this 5 into the summation. We're allowed to do that. Anything that doesn't contain n, you're free to move in and out by multiplication or division. So this does not have an n. I can move it back in. And it's in a denominator, so it's going to bump up the power of 5 in the denominator by 1 more. And eventually looking like that. So what we did here is we took this pretty ordinary looking function, turned that into a power series. Okay, for now, let's not talk about why we do that. We'll see that in a little bit. But let's get used to being able to do that. Any question with the steps up to here? Okay, now we need to talk about the radius of convergence. Obviously, every time you write out a power series, we need to know where this series will converge. Anything outside that, this series is completely meaningless. So how do we find that? There are many different ways. Give me one way to find the radius of convergence. Ratio test is one way. Is there an easier way? Yeah. Geometric, excellent. Right? Look at this thing on the upper right. The geometric series says that this x has to be strictly less than 1 when its absolute value around it. Here, we're applying the same principle. This guy is our x now. So we require this to be less than 1, according to the rule for geometric series. So that means x over 5, absolute value is less than 1. Absolute value of x is less than 5, right? Multiply 5 across. So x must be strictly between minus 5 and positive 5. So the radius is 5. What about the interval? Do I need to check the endpoint? We could do that, but we actually know we don't need to check them because we know geometric series has to have this thing strictly less than 1. So because we're borrowing the consequence of using a geometric series, this has to hold true. And that means we don't have to check the endpoints. So no need to check ends because of geometric series. Right? This. We know geometric series will diverge when it's exactly equal to 1, which happens on the boundary points. So therefore, we already know this will diverge if we go to the endpoints, and therefore we don't need to check the ends. Questions? Okay, let's do a few more. We're going to take advantage of the geometric series over and over again. Let's try this one. X over 3x squared plus 1. Again, we're going to massage that thing so it looks like a geometric series and force it to work. Right? That's the basic idea here. As long as it has the basic resemblance of the form, we can do something with it. First thing to note is we have a 1 on the top. So this x over here is getting in the way. Let's rewrite it. And the downstairs, I'm going to do this. And that's why we did the factoring out of this. And downstairs, we wanted to look like 1 minus something. We already know how to get around this 1 plus something. So this is 1 minus negative 3x squared. Okay? All right, then we know what to do with this thing here. We'll worry about this x after we get a series out of it. So we'll take care of that right now. So this guy turns into summation n0 to infinity. And once again, this is our x. in that formula. So it turns into negative 3x squared to the n. All right? Questions so far? Good? Good. All we're doing is just doing algebra, changing one variable to another. And once again, let's break things up. Let's write this explicitly as a alternating series with a minus 1 to the n, 3 to the n, and then x to the 2n. And just like last time, anything that doesn't have n can be moved in, out of sigma by multiplication. So these guys cannot come out. They have to stay inside the summation. They all have an n attached to them. But this doesn't have an n. Let's bring it back in. And inside here, x already has a power of 2n. We'll bring one more into here. And that makes it x to the 2n plus 1. Yep? So there we go. There's the power series representation of this thing right here. And you can write out a few terms if you want to see explicitly what it looks like. Again, we have to make sure this makes sense by writing out what the radius of convergence is. And just like last time, you go to the convergence property of geometric series. It says that the absolute value of x, in quotes, which is this guy right here, must be strictly less than 1. All right, the minus sign doesn't matter because we're doing absolute value. That's divided by 3. And take the square root. So there's my interval. Oops, I'm missing a sign here. And my radius is 1 over radical 3. And now we must make sure to use this infinite series here, we have to have x strictly between these two numbers. Anything outside of that, the series will diverge and therefore is meaningless. But anything inside this interval, the series converges and will behave just like the real function, exactly like it. Questions? Good. All right, let's try this next one. This one has a little bit more, well, not more, but a different kind of complication involved. Here we have 3 plus x over 1 minus x. And once again, the only weapon we got is this. Right? It's like when people say, if all the the only thing you got is a hammer, then everything starts to look like a nail. That's the same thing we're doing here. This is a hammer we got, and everything is a nail. Yep? Okay, so now how do we make that look kind of like that? Break it by how? Good. All right, so we saw what to do with the x before, right? We want the numerator to be a 1. So the 3 is easy to take care of. The x is relatively easy to take care of. Take out the 3. Take out the x. And now the denominator is already in the right form. There's no special x to play around with. So we just go directly and change these two series. 3 summation 0 infinity x to the n plus, so that's one series. The next guy, x times summation 0 infinity x to the n, that's the other series. Once again, anything without an n can be moved in and out as you please. So bring it in. This one here becomes x to the n plus 1, right? All right. So this looks pretty good. But what we want to do here is to combine these. Combine into 1 if possible. And 1 summation is easy to deal with. 2, all right, but when you got 18, then you got a problem. So we want to get these combined into 1. So take 1 minute. I want you to think about how we can do that. Okay? And as usual, if you get lost with series, write a few terms out. Find a pattern and see if you can get these things combined into 1 summation notation. So whatever you got in the end, you should have only 1 sigma. So give it a shot. All right, closing up. Who's got an answer? What do you got? Plus x to the n. Close. Who else has something like that? Close. All right, so remember I said, if you get lost with series, write a few terms out and look for a pattern. So let's write a few of these out. Starting with n equal to 0, this is 3 plus 3x plus 3x squared plus 3x cubed plus dot, dot, dot. Right? That's the first series. And the second one here, when n is 0, we get x to the first. And then n is 1, we get x squared plus x cubed plus x to the fourth plus dot, dot, dot. And what you should notice here is that after the first constant, everything else can be added together. There is a 4x squared, 4x cubed, 4x to the fourth, right? Do you see that? Plus so on and so on. So this is 3 plus 4x squared, 4x cubed plus 4x to the fourth, and so on, right? Now the 3 we can't do anything about, but this we can write as a summation. And how would you write that in a sigma notation? To the n plus 1, right? See, what's wrong with n alone? When n is 0, we get a 4, but it doesn't belong here, right? So we need to go up by 1. Very good. Could we do this? Is that okay? Yeah. So you can do any of these two, whichever one you feel more comfortable with. Yes? So how did you do it? Why don't you tell us how you did it? Here. Third, okay. Here, yeah. Okay. Like that. Like this. And then you multiply this into here. So what did you end up getting at the end? Say that again. Okay. Yeah, you could do that, but it comes down to which one you consider as simpler. So you're right. I'll take back what I said earlier. What you had is correct. Correct, yeah. But it's preference now in the end. This is usually the kind of thing we expect to have when the stuff inside the summation is as simple as it can get. Usually. Not always, but customarily when you look up series, this is kind of the form we will see. Even though this is perfectly okay, but this is what you will see more often. And that's what WebAssign would expect. Okay? So good question. Other questions? All right, good. Let me show you one more example, and then we'll talk about what is the point of all of this. There is a point, believe me. We do this for a reason. It's not just to torture you, but that's part of it. That's a joke. Oh, come on, guys. All right, so let's look at this one. That's a 16, sorry. Okay, so we're going to, again, you have a hammer. This is the hammer you've got. And you're going to make everything look like a nail by making that work. All right, so ideas. What do we do? We have a quadratic here. I would love to have a linear down here. What tool did we use before to break things up like that? Partial something. Partial fraction. Very good. So here's what we do. You factor the denominator downstairs. So I won't carry this completely out, but just to show you the basic idea. So by partial fraction, we get this thing. Okay, and then you deal with this thing, making it look like 1 minus x, factor the 10 out, factor the 6 out, 1 minus quote x, get 2 series, and so on. Okay? So see previous examples. Okay, does that make sense, the idea here? Right, the step you have to do, obviously, it can be a little bit involved, but does the basic idea make sense? Yes? Yes? Yes, good, thanks. And it turns out that we can integrate and differentiate all these things the usual way. So for example, I use A. What is A power series representation of one over 5 plus x, the whole thing squared? So first of all, notice because of this squared here, we have that. But you cannot simply just square everything. Right? It doesn't work that way with power series, at least not that simply. There's a little bit more things involved. So what happens here, because all of these have multiple terms, when you multiply two polynomials out, for example, you have to FOIL things out. So it's not just each term individually squared. Right? You see the reasoning why this doesn't hold true? If you use two terms, you got to FOIL that, and that's not the same as the whole thing squared. So we can't use that to take care of this. But what we can notice is that one over 5 plus x, the whole thing squared, is equal to the derivative of negative 1 over 5 plus x. And we dealt with this one in the first example today. Right? We ended up getting this thing right here. So this is the derivative of, I'm going to borrow from example 1, what we already had. Negative 1 times the summation 0 to infinity and minus 1 to the n, x to the n, 5 to the n plus 1. So this. from first example today. Okay? So we already know how to do that part, which we did separately. And now I want to take derivatives. So how do we deal with this minus 1 then? I'm going to bring it in. Yep, that's a good idea to do. Bring it in. So this will become minus 1 to the n plus 1, right? X to the n over 5 to the n plus 1. All right, questions so far? We're good? Okay, now I want to take derivative of this infinite series. Once again, let's write a few terms out, differentiate term by term, and come up with a pattern, and then collapse back into a summation notation. So what we got here is the derivative of just a few terms. First term is, what's the first term? Minus 1 over 5, right? What's the next one? Positive 1 over 25x, right? And then what? 1 over 125x squared, and 1 over 5 times 125, 625. Good enough. And so on, right? Just always remember, if you don't like series, write a few terms out. You know how to deal with this, even if you don't feel comfortable with dealing things in a summation notation. That's okay. Take the derivative. The first one is a constant. It disappears. The next one is 1 over 25. And then minus 2 over 125 x plus 3 over 625 x squared, right? And then this continues on. Downstairs, these numbers are getting big, but there's a pattern here. This is 5 squared. This is 5 cubed. This is 5 to the 4th, right? So the next one would be, what would the next one be? Let's just write it out. What would the next one be? 1, 2, 3, 4, right? There's the pattern I see. And then downstairs would be whatever 5 to the 5th is. See that? And what's the power of x? 0, 1, 2, 3. Okay? We're looking for a pattern. There's always a pattern. They may be complicated, may be simple, but there's always a pattern. Look for a pattern. Now we collapse this back into a summation. This is possibly the hardest part to do it. Possibly the hardest step. Okay, so let's start with a summation from 0 to infinity. Look across these terms. Give me one thing that should be in here, that has to be in here to give me this sign. Minus 1 to the something, right? So we want the first one to be positive, and that's when n equals to 0. So if I do this, would that give me the right alternating signs? Yes? Right? Minus 1 to the 0 is 1. So this is positive. Minus 1 to the first, that's this guy right here. That's negative. Positive, negative. So this is okay. Yep? Okay, so what's left? What else do we need to have? How about the numerator here? How do we express that? Plus 1, right. When I want to start with n equal to 0, I want a 1 up here. When n is equal to 1, I want a 2. When n is equal to 3, I want a 2, I want a 3. 3, I want a 4. So do you see why it's n plus 1 on the top? Yes? How about downstairs? Five to the n plus 2. Good. We start with a second power. That's when n equal to 0. And then we go up by 1 each time. Okay, and what's the last thing here we need? X to the n. Very good. The first one is no x, so that's when it's power 0. First power, second, third, and so on. Okay, so remember, this was when n is equal to 0, n equal to 1, n 2, n equal to 3, and so on. So there is our power series representation. Radius of convergence. This, yeah, question. Yeah, you can start with n equal to 1 and then adjust these things. Yeah, absolutely. On WebAssign, however, they want you to fill in the box with this already provided. So they force you to start at 0. But on the quiz, when you have to write things out yourself, you can start with 1 if you want. In fact, you can start with 18 if you really, really want to. There's no rule saying you can't start with 18 or 608 if you really want to. You have the freedom to start the series anywhere, but often it would be the simplest to start at 0. Okay, radius. So radius of convergence is not affected by differentiation or integration. But the interval may change. In other words, the endpoints may be included. Anytime you start with a power series and then differentiate or integrate it, the radius stays the same. The only question then is the new series might be okay to include the endpoints, whereas the old one is not, or vice versa. But to answer the question about the radius of convergence, we simply look up the radius of convergence of this guy right here, which we did earlier. Does that make sense? Yep. Good. Okay, let's do one integration, and then we will end it there. So here we have natural log of 5 plus x. So obviously, the geometric series is not going to help us. 1 over 1 minus x, there's no way we can make it work in here. However, notice that if I integrated what we had earlier, then I get natural log of 5 plus x. And let's assume x is positive here so we don't have to deal with the absolute value. Okay, so now I'm going to take advantage of what we had before. So this we know from the first example, minus 1 to the n, x to the n, 5 to the n plus 1. Now we integrate that. And just like the case with differentiation, get a few terms out of here, out of this summation, integrate the normal way, and then come up with a pattern. Once again, if you don't like dealing with that, that's fine. Just write out a few of these. You know what to do with that. Okay, next. This guy turns into minus 1 over 5 with an x attached to it, right? I also gain a constant. Because I'm integrating something, I gain an arbitrary constant. I'm going to put it first. Since I'm going to rearrange these into ascending order of powers of x to the powers of x. So next one here would be plus 1 over 2 times 25 x squared, right? Minus 1 over 3 times 125 x cubed plus 1 over 4 times 625 x to the 4th, and so on. And the reason why I didn't multiply the 2 into 25, the 3 into 125, and 4 into 625 is because we're looking for a pattern. And here, notice the pattern here. This is 1 over 1 times 5 to the first. 1 over 2 times 5 squared, x squared, minus 1 over 3, 5 cubed, x cubed. So then we collapse that into a summation, starting at 0 or 1, whatever. Actually, 1 would be a little bit simpler here. Let's do 1. If I do 1, notice that I still need my minus 1 to the n. The first one gives me a negative, positive, so on and so on. And then the numerator is always a 1, right? And downstairs, notice the way I broke these up. It's n 5 to the n. See that? When n is 2, it's 2, 5 squared. When n is 3, 3, 5 cubed, blah, blah, blah. And then finally my x to the n. So what we end up getting here is that natural log of 5 plus x can be expressed this way. And how would you find c? 1 second. How would you find c? My sign is wrong. So what should this be? Oh, you're right. I got these all completely backwards, right? Oh my God. What am I doing? Okay, so plus. Why didn't you tell me earlier? How do I fix that then? How about I do this? Is that going to fix it? Yeah, that's going to fix it. Okay, to figure out C here, you plug in x equal to 0, because these have to be equal. When I put in 0 here, I get natural log of 5, and all of these guys go away, so C has to be natural log of 5. All right. Okay, that's it. There's a lot of stuff I understand, but that's it for today. We'll do more of this next time.